All right. So I guess before we get started, I sent out an announcement. I'm assuming everybody got it or saw it or whatever. So the midterm exam is up. I need it submitted. So do it online over on your own time. I won't give you assignments over the weekend. Um, it's due before class starts on Tuesday. I put up a practice exam, which does not count against you. So you can take the practice exam and see what the exam might be like. Then go and learn the stuff that you struggled with. Then go and take the regular exam. They should take less than an hour, I would think. Remember, if you do better on the final than you do in the midterm, I'll replace what you got on the midterm with whatever you earn on the final, but not the other way around. Only goes one direction. All right, questions about that? Make sure you get it in before class starts Tuesday because I have to have grades in by like midnight on Tuesday. Otherwise, registrar comes and yells at me. It's up. I think it's up now. I put it up yesterday afternoon. Make sure you read the line. One says practice next to it. You can take that as many times as you want. It won't count against you. Um, they are extremely similar exams. Just the questions shift a little bit, but they cover the same topics. All right. So let's keep going from where we were talking about yesterday. I want to finish up our time complexity discussion, and then we'll get back into classes. I also want to close a couple of loops with the differences between Python and um, these C-based languages. You know, you've heard me say multiple times that I'm not a big fan of Python, and part of it comes down to teaching with the language, not that the language itself is bad. So I want to bring awareness to a couple of things that I think hurt the teaching experience. I'm going to kind of force this in one direction, but you'll see when we get to it. All right, so last class we were talking about this concept of time complexity, that certain things, the worst ones are when something looks easy, then if you assume that you're in some sort of infinite loop because it's taking forever for your code to run, and then you start fixing stuff when actually you had the right math before, it just happened to be a time complexity problem that you wouldn't have guessed. So we purposely picked this reducing fractions problem because it doesn't seem all that scary. It's not like it's not rocket science, if you will, yet we saw that it was a major time complexity issue. Um, Now, I'm going to skip, we'll come back to the dice roller here in a second. So we introduced this Euclidean algorithm, which is made by a math guy. And effectively what that algorithm says, if you have two numbers, 48 and 18, for example, the numerator and denominator, there's a fact. The fact is the biggest number that divides both of them is the same as the biggest number that divides 18 and the remainder uh, uh, when 48 is divided by 18. So it's kind of that little tiny thing that the mathematician noticed that allowed us to test a number. And if that fails, we could take a giant jump through the numbers, skipping a whole bunch of numbers we would have otherwise tested, and then try again. Then if that doesn't work, skip a whole bunch of numbers that the other one would have tested. Try again. All right. So it happens to be kind of the math trick behind what does it mean for something to be the greatest common divisor of two numbers. All right. Unimportant how it really works. We just saw that it made things way faster. That was what we visualized, right? We went from we're not waiting for this to finish to it seemed to finish instantly. And I want to kind of put that to a picture here in a second. Um, in computing, and it's not something that I'm ever going to test you on. It's actually something that was way more important years ago for reasons that we've already discussed in here. Computers used to be slower. Computers used to have a lot less memory. We don't really have resource issues today for it largely. So modern programmers tend to not think about some of these it's not that common that we run into time complexity problems. Every blue moon, we bump into it. So we want to kind of be aware that they're out there. But in general, we don't have to worry about this stuff too much. And when you get to problems like this in the real world, you'll already be an advanced enough skill set in order to be able to do it. Yeah.
Slightly off topic, but when we were doing dice roller assignment, there's like, and there's indentation that is required for both the method and the function.
Okay.
So it's like odd, and I'm not exactly sure, like.
Okay. Well, we're going to do it here in a few minutes, but there's nothing new with indentation. Python's just very indentation specific. Things have to go with stuff. All right. So in our original version of trying to find the greatest common divisor of two numbers, we just did a brute force thing, right? We said, which of these two numbers is smaller? That's the biggest number that might evenly divide both of them. And then we just kept trying numbers, counting all the way down to one, knowing that, well, it's at least going to be divisible by one. So we would call that order the minimum value of A and B. So this, when somebody says big O notation, that's what they're talking about. The speed of this thing. The more generic term for this would be linear time. Effectively not that fast. Computer makes up the difference for us. All right. Now, the Euclidean algorithm, as we saw, much faster. It doesn't test a whole bunch of those values like I just mentioned. Okay. It operates by jumping through a whole bunch of things just based on how the algorithm works. And this takes us into another type of order called logarithmic time. All right. So this is still the minimum of A and B. We're still operating off of the smaller of the two numbers. It kind of makes sense. The biggest value that evenly divides two values can't be bigger than the smaller of those two values. Decent enough starting point for that. All right. But from there, it's the log of that. And it's easier to visualize here on the next screen, but this last sentence talks about, as the size of the problem gets bigger, the number of steps only grows a little bit in logarithmic time. As the number of things you're comparing gets bigger in linear time, the number of steps also linearly goes up, so it gets way slower, way faster. Go ahead. Yeah, but here's like an example. So this is specifically using, GCD as the thing. So if we had 10 numbers we were iterating through, that's going to be big O of 10, big O of n. So if over here is, if we call this n is 10 or n is 100 or n is 1,000. So linear time means we're going to have on average, that number of things we need to check. That's the speedometer of it, if you will, and not even on average. The potential worst case is what it really is, not the average. Okay, so worst case, we're gonna have to check all of them, is linear time. Notice in logarithmic time what happens here. As our number goes up here, linear time goes up by the same rate. But logarithmic time, we went from 3 steps instead of 10, to 7 steps instead of 100, to 10 steps instead of 1,000, to 20 steps instead of 1,000,000. You're starting to see that speed up. And we felt it last time when we ran the code and saw it just instantly finish. All right. Probably in the early-ish 2000s until maybe 2010, this idea of big O was kind of important because you really needed to think about the efficiency of your algorithms, even for less complex things, just because our computers weren't as capable as they are today. But now our machines have, 6, 8, 10 different cores. So you have a bunch of processors all capable of working on stuff. You got a bunch of RAM. These just don't come up that often. All right, so questions about this idea of, I don't know, deciding the speed of different algorithms, or try to kind of consider how fast an algorithm is if your program seems slow. Really, the sticking point is, don't just assume your code is wrong if it feels like your program's in an infinite loop. It might be. You might have made a mistake or forgot to increment a value or something like that, and you are in an infinite loop. But it could also be that your math is right, but the problem you're working with happens to have some complexity hidden inside of it. All right. So then let me spend a few minutes talking about some Python caveats. And really, this isn't just Python. You can take most of what I'm going to talk about here and apply it to any loosely typed language, any loosely typed interpreted language. They all kind of follow by the same rules. And part of it is when you're going through your code line by line by line by line, not pre-compiling it, something has to give. Okay, we start off with this idea of variable scope. So variable scope is a fancy way of saying, when I define a variable, where can I access it? If I define a variable inside of a function, I can only access it inside of that function. If I define a variable globally in my program, I can access it anywhere in my program. Now, I want to jump over to some code here. Now, what we had been doing up to this point, let me make the font a little bit bigger here. We see that? All right. So what I had previously been doing, because we have this idea that I'm trying to connect all languages to each other and saying that all programming languages, all programs begin and end with main. And that's largely a truth. We saw that, hey, there's this weird thing built into Python that has the word main in it. These are called Dunder methods and Dunder words. Double underscore is what that means. But it is a truth when we say that all programs begin and end with main. The issue here is that this if statement, as I have it written, is sitting out there globally in the entire program. Which means if I define a variable in here, if I say s is equal to hello, and I'm going to actually create another function real quick, def do something. We'll print out s there. Let me hide this guy. So we're going to do several different examples and see where it breaks. All right, so we see s is hello. My program, well, we printed out hello world. Oh, let me print s, sorry. Oh, I'm printing s up there and do something. I forgot to call that do something. All right, so I defined s here inside of this. I've advertised it as being a function. All programs begin and end with the main method, the main function. But the way we've actually written it here isn't a function. It's just this random if statement sitting in the middle of your Python program. Like she was asking a few minutes ago, indentation in Python is really, really, really important. See how this guy is left justified? That means it is at the very, very, very top level of this Python program. All right. And because this code executes, this is the code that is actually running. These are all just definitions, right? These are defining functions that we may or may not ever call. In fact, as of right now, I'm never calling this function here that I just happen to name main. That'll be the follow through in this example here. Okay. So really what my program does is those 3 lines of code there. Even if I take out this name main thing, you know, we kind of put that in there to drive home this point that all programs begin and end with main. If I take that out and I just have random code sitting there left justified, this is happening at the global scope in our program. So if I run this, we're going to see it's going to have the same output. Okay. There was nothing special about that thing being inside of main other than, put it back in there. If I take one of those underscores out, we see my program no longer has any output. this code right here, because it's indented inside this if statement, only occurs if this Boolean expression is true. When I had this as a dunder word, underscore, underscore main, underscore, underscore, that is a magical word built into the Python language that indicates that the thing that was automatically called when this program ran was main. All right, so that means this code right here only happens if the name of the thing that was originally called also has the underscores. That's another magical word built into Python. This code only happens if this Boolean expression is true. So since we run it right now and we see, oh, it does happen, that must mean that this Boolean expression right here is a true statement. But if I change one little, I'll just take one underscore off there. I have a typo. Okay. All of a sudden, we're not referring to the right magical word that was built into Python to represent this concept of main. And now you'll see that this code only executes if this Boolean expression is true and it's no longer true. So we have no output there. If I take that out completely and I just say, this no longer conditionally occurs. This just always happens. I'm no longer saying if you're in a place, do this. I'm just saying do this. It's left justified. It's part of the entire program. Now just run it. When I do that, it always is going to run every single time. All right. So I'll pause there. Go ahead.
So double underscore, that little if statement there, like pretty much very similar to like the public static main void.
It's not, and that's kind of my point here. So if I put this back in there, I'm trying to accomplish the same thing with it. So I'm going to have a workaround here so it actually accomplishes the same thing. So her question here is that guy right here, and what I just heard you say is probably Java code, right? So you're used to seeing public, static, void, main, string array, elephant, something like that. Now, args, why do you think it's called args? Yeah, it's the command line arguments. That's just the name of the variable. Whenever I write it, I always write it as something else. It doesn't have to be called that way, but it does need to be a string array. It's a variable name. You could say LOL. It's just like if I have a function here and it takes in a variable called S. I could change it to hello or LOL or whatever I want to name my variable. So it does need to be of that type. It does need to be called main. In Java, it does need to return nothing. We're looking at code from a strongly typed language here, not a loosely typed language. That's why we have types for our variables. We have return types. We have a bunch of extra fluff there, which I'm telling you is better. If you think through code in terms of the types, then you look at languages like Python as kind of being convenient for quick code, but not really great for teaching. But in any case, from your question, this is the header for a function. In fact, I'm going to go ahead and just finish writing this. So this would be something like system.out.println hello world. So this guy right here, if we were writing this in Java, would be what main looks like. Every single Java program begins and ends with main. You can have one file that has main in it. It must be public, and it goes and finds that main method, and it starts there and does whatever that guy tells it to do. He might transfer control over to another part of the program, and then you're in some functions over here, but ultimately you'll always make it back to main for the end of your program. All right. What we've done in here to try to mimic that isn't with the same kind of animal. I said I'm replacing an entire function, an entire method, with just this if statement that takes advantage of our super secret word built into Python for this underscore underscore main underscore underscore thing. We see that Python's trying to do this main method thing. But because this is all happening at the global scope level, that means this variable S, the entire program knows about that variable S. All of my functions know about that variable S. If I try to create a variable in one of my functions called S, I'll break S. It won't be a different variable. I can't say, oh, this is actually a different version of S and I want it to be local to this function. Because I already have a global one, so I'll be overwriting it. So if we really want to get the equivalent of this, let's move it down here. I would write a function in Python called main, and then all I would do is I would still have my if statement here, since that's the magical way for us to jump on the main bandwagon. But instead of defining things here, I would just transfer control to our main function that we wrote. And now scoping rules will work the same as any other language. If I define S inside of main here, and then it's going to scream at me if I leave that guy in there. So let me do that. And then I call do something, which tries to print out the value of S. Now we see that it's complaining. Oh, hold on. Do something wants me to give it a variable. It is complaining, but it's complaining about a different problem. Now you see it's complaining about the right problem. This line right here, print S, no longer knows what S is. It's saying name S is not defined because S came into existence here inside of a completely separate function. It lived and died with that function. We would say its scope was local to that function. Whereas if I had defined it just inside this if statement, now it knows about it. This version of S is local to main. So actually it's a waste of time as I have it written right now. In fact, here, let's just so we see that. All right, so in here, S was equal to a hello, and that version of S died as soon as main ended. So I kind of wasted my time creating it. But then when I call do something, and I went to print out the value of S, the value, it looked locally, it said, is there a variable in here called S? No, we didn't define anything in here called S. So it goes up to the next level up. Where else can I look? It looks at the global scope, the variable environment that governs the entire program. Things that are left justified. And it sees that, oh, this dude did define a variable called S there. So I'm just going to go ahead and print that one out. All right. This isn't how normal programming languages work. So I'm going to say from this point forward, so we can drive home the idea of scoping rules, so that when you transfer from language to language to language, your knowledge will transfer with you. We won't just rely on the magical if statement. We will just have our magical if statement hand off control to an actual main method that we're writing. You don't even have to call it main. You can call it, woot or whatever, but we're purposely calling it main because I have that saying, all programs begin and end with main.
But if I have a class, right, that has main, class that's going to be, working with it, do I have to include that if underscore main inside
No,
that class?
and
Or can I just call my call?
any answer I give right now is going to be so situational. So when you see an example like that, ask me. The short answer is no. It ultimately comes down to scoping rules. There's nothing special about the word main throughout your program. Anything you write that says the word main isn't special. We just happen to be naming our stuff main because that's what other languages do. This is the only super secret thing that Python has built into the language for accomplishing stuff like this. Make sense? And you'll see from examples. I'm just trying to force Python to behave like our strongly typed languages so that when you transition between those two languages, nothing's wrong with doing Python this way. Nothing's wrong with having a little bit of organization for how your program takes off on the launch pad. We're just doing some additional organization because Python doesn't put it in there for us. All right, so whenever you see an example, let me know, and then I'll explain it in the context of that example. All right. So that covers this whole variable scope thing. Scope is where is a variable accessible? We want to have control over when we create variables and when those variables die so that we can have multiple variables in our program that maybe have the same name. For instance, if we have a giant program and we sometimes need a variable to just temporarily hold a number, we might call that variable temp, right? We don't want our temp variables fighting with each other just because they happen to have the same name. We want them to be local and die as soon as that's over, so we need to be able to rely on scope. All right, I'm going to skip this for a second. We already kind of mentioned this idea of dunder. There's a whole bunch of dunder methods. I've only showed a few here. There are things built into Python as well as other languages. I think somebody brought it up last time when they talked, somebody mentioned, is that like the two-string method? I don't remember, was it you or maybe him behind you last time, but built into Python is a whole bunch of these double underscore method names that are already implemented, but that you could choose to re-implement, to override, to do your own stuff. And let me show that by an example here. So we're going to say class. Call this player. And well, we've already seen one of these dunder methods that we always override. Because if I don't do anything here, Python actually makes me write something under this guy. But if I do like do something, then I just print hello or whatever. Get rid of this guy, this guy. All right. So I created this class called player. Notice I have omitted something that we've put in every single class that we've written up to this point. Up to this point, we've had this little underscore init underscore. Okay. That is one of these dunder methods, double underscore methods, double underscore before and after. And it is how we represent our constructors. Yet we see here in main, I'm already doing our little trick, right? My if statement's here. All he does is transfer control to an actual function. So this is main. We see in main, I'm saying I'm going to create an instance of player called P. Then I'm going to print out P. And we see that it gives me something that looks like that, right? That is the default behavior of constructors. The default behavior of a constructor is it goes ahead and establishes this object so that, well, it makes this syntax right here work. If I don't choose to write my own constructor, this syntax still works. Instances of things of type player can exist. All right. And from there, I can do something like p dot do something. And we'll see that it calls the function that lives inside that guy that just puts out hello. All right. Now, if I say print self dot name, for example, we have a player. It sounds like players might have names. Maybe that's kind of where we're going with this thing as we get into our Dungeons and Dragons thing a little bit. I'm jumping ahead of our dice roller, but to kind of connect some dots for us here. Okay. It's yelling at me. It's saying, hey, I've never heard of a variable called self.name. Scope. Variable scope is what we're seeing there. It looks inside of do something. It's going to look at the local variable environment. It's going to say, okay, you did not define anything in here called name. And self, this global way, self is how an object refers to itself inside of itself. It also has never heard of a variable called name, because we missed our opportunity to do that. If I decide, you know what, a player object, when I build one of those, he's a little bit more than just a generic plain Jane object. There's more to him than that. For example, we've decided that players probably should have names. So we might come in here and say, well, we're going to go ahead and override the init method. There exists this dunder method called init, and we're going to override that. We're going to put self at the beginning because that's how you do it in Python to make object-orientedness work. We'll take in the player's name there, and we'll set self.name equal to name. So rather than letting the default init function that does nothing do the job for us, we are now writing our own version of init, which will do the job for us. Now, I'm purposely not changing something yet. So if I run this now, notice it is screaming at me. It's saying, hey, you've gone ahead and tried to create an instance of player, P equals player, no just parentheses. What that guy is trying to do is he's trying to call the default constructor, the default underscore init function. I think somebody last class, I think it was, you're the Java programmer, right? You were asking, does the constructor need to be the same name? In most modern languages, most C-based languages, our constructors are not called init just generically. Your constructor would have the identical name to your class. Java, and C#, we would have, instead of it being called init, it would be called player. That took in name as a parameter here, and we would say this dot name is equal to name. That's the Java equivalent to this guy right here.
You think that it's because default B equals player inside main?
Yeah, well, let me go back to the error now. I just wanted to connect those dots right here. So in most of our modern languages, when you write a constructor, the constructor must be named the same as the class name. Python, your constructor must be called underscore init underscore, because you are choosing to override the default constructor with something more specific to this guy. Go ahead. So he's asking if I choose not to use init. So if I let me do it in 2 steps here so I can put it back easily. So if you choose not to write your own init function like that, he wants to know, well, when I build a function, can I give it things? Or, can you give it parameters? You've missed your opportunity. You can no longer give it fields. Your chance to bring fields into existence is through that init constructor.
So you need that in order to call P equals player with the parentheses and to make that instance of the.
Well, so now that I put this guy back, first decision here, I'm saying, okay, you know what? A player is a special kind of object. So we've been talking about this idea of object-oriented programming, right? Let me kind of show you a little picture here. And this is true of all object-oriented languages. And actually, Python is kind of a cool language from this perspective because I'm kind of telling you how languages are built. And with Python, it didn't start off as object-oriented. So what we're seeing is somebody bolted on object-orientedness onto Python and just kind of made it work. That's what that passing in the self thing is. But every object-oriented language will have some top-level object that's built into the language. He's born into the machine called object. Might be a lowercase o, might be an uppercase o, but there will be something built into the language that is a generic object that has stuff in it that is only, and I'll go ahead and I maybe had even shown this before. Oh, and actually, I'll even show you getting to it. All right, so we can see it here. So we're used to dealing with strings. I'm looking at Java documentation. Java is not actually my favorite language. It just has really good documentation. So their documentation is very organized, so it's a good thing to use for this example. It's actually what makes Java, I think, such a popular language is how good it's documented. So we know what strings are. We've been messing with strings all semester so far, that kind of stuff. So it doesn't surprise us that strings also exist in Java. Probably seems like most languages probably have strings. Now, up at the top here, and again, as you become more and more advanced as a developer, you'll get more and more used to looking at documentation. This is a really important skill to be able to read documentation. I promise you, you're not going to memorize every little thing about every little language. Okay. And then once you start learning more languages, they'll get all crisscrossed in your brain. And then you'll have to figure out what language am I coding in today. But then you could fall back on the idea that they're all kind of the same. But in any case, we see that the name of this class is called string. But above this guy, there's this thing called java.lang.object. That was written by the people at Sun Microsystems. That was born into the Java language. When they built an object-oriented language, they created this top-level thing called an object. And every single object that will ever exist, whether it's more objects that they wrote or it's objects that we wrote, will at some level be an object. And we can see it. So if I do let's do Java buffered reader, I think that'll get me to yeah, so at least gives me one more level. So here's something else called buffered reader. Don't worry about what that means, but we see that a buffered reader is a reader, which is an object. So, but when somebody at Sun Microsystems, when they wrote buffered reader, they wrote it in terms of something that already existed that they also wrote called reader. But reader was written in terms of something that's built into the language called object. So if we click on object here and we scroll down, we see this is what in the Java programming language, they've decided is the minimal stuff that makes you an object. If you don't at least have this, you're not an object-oriented language. Now, most developers will not use a high percentage of these either ever or very rarely in their lives. I'll walk through them real quick. I think it's good that we're not going to get to some of the stuff because I wasn't giving you homework over the weekend anyways because of the test. But all right. When I say pass by value versus by reference, does anybody in here know what I mean by that? It's a programming concept, but we haven't, again, I don't want to just always be complaining about Python. It's tough to teach with. But anybody want to take a guess what this means? All right, so it has to do with when we're calling a function. When calling a function and passing an input, parameter, or whatever you want to call them, some types are passed by value, which means a copy of the original value is passed in. Some types are passed by reference, which means a pointer. What's a pointer? Remind me what a pointer is. Variable that holds a memory address. So if it's passed by reference, that means a pointer to the original value is passed in. Now, this is an important distinction because if something was passed in by value, if I change the value of the parameter, that change will disappear when the function ends. Okay? Because I gave it a copy. So if you come up to me on the street and ask me for a quarter, as if people carry change around, but if I had a quarter and I handed you a quarter, and then you went and melted it down somewhere, would it impact the other quarter that's in my pocket? Now, I gave you a copy of a quarter. Yeah, it's your own quarter. Do with this what you will. It's not going to impact me moving forward. Okay? But let's assume you're having a party at your house. And obviously, you invite me to the party. I'm a life of party. Um, and do you hand me the house and say, open the door at 8? Actually, young people probably start parties later than that now, right? 11, open the door at 11. Well, you're a little older. we're in bed by 9:30. So that would never make sense in real life, right? Okay. You would never hand me an entire house and tell me to open the door at a certain time. Why not? Why wouldn't you hand me a house? Some of you look fairly fit. Do some gym time. Houses are really, really heavy. Even the tiny homes, you're not handing me one of those guys, right? Okay. So because some things are really, really big, the equivalent in computers would be they take up a lot of memory, right? Because something is really big, we might say, you know what? Rather than me handing you this giant thing, I'm going to just hand you a memory address where you can find it. And then you can go and do whatever you want with it. Okay. But that has consequences. Okay. Let's assume that you take this midterm exam and I've been unfair and you fail it and you're all ticked off at me and you find out the address where my house is and you go and spray paint it. I'm going to be in for a surprise when I get home because you've gone to the actual place in memory and made changes to that value. Make sense? So one of these isn't necessarily better or worse than the other, passing by value versus passing by reference, but there are consequences to those two things. Now, built into languages, we had talked about the primitive types. So if we say pass by value examples, primitive types are typically passed by value. So if I'm passing in an integer and you make changes to that integer, it will not be felt outside of there. Let me kind of show that here. All right. So we're only working with these two functions right here. So inside main, all programs begin and end with main. And remember, we are calling main from our magical little if statement there at the bottom. We'll just kind of forget that that guy exists, but 100% of your program should start like this right now. All right. That'll put you in line with other things. So then we have main. So inside main, the first thing I'm doing is I'm defining a local variable, X. This variable lives and dies with main. But since main's the quarterback of our entire program, not a big deal. I'll go ahead and print out the current value of X. We expect that to print out a 5. It was a 5 one line before this. It's still going to be a 5. Then I'm going to go ahead and I'm going to pass X into my function called try to change. Now, X holds a number, right? So X's type is like an integer type, which is one of our primitive types. Now, I have advertised that primitive types are typically passed by value by default. All right, so I'm passing in the current value of X here, which is a 5. 5 comes in for some num. I'm then printing out the value of some num, which should also then print out a 5. Then I'm going to change some num to a 7. And I'm going to print out some num again. It's going to print out a 7. But then this function ends. And I fall back out here to main. And this line right here just finished. And I'm going to print out the current value of X. So the question is X the changed value of 7? Or is X the original value that was 5? Because it's a primitive type. We expect that all these changes here died when this function ended. It was working with a copy of X, not the original. So there's my original 5 right here. Then I call try to change. Here's the first time I printed out some num. That's my 5 here. Then I changed some num to a 7, printed it out again. It says, oh, it changed. It's a 7 now. Then this guy ended, and I printed out the current value of X, which has reverted back to 5.
What print something at the end of try to change?
It did.
Did?
This is the first print right there at main. So that's this guy right here. Here's the first print inside there. That's the next 5. Here's another print. That's the 7. And then here's the final print, which is that last 5. So really, it's these last 2 that tell the story. I changed it to a 7 in here, but after this function ended, it was back to a 5. That tells us that numbers are passed by value. A copy was sent in to try to change, which would never have an impact on my original. Go ahead.
The function node to end without like a return or something.
Just ran out of stuff. Yeah, so online folks, he asked, and you're like what I think you're asking in terms of try to change, but the same thing's true with main.
Yeah.
You know, he said, well, how did this function end without you saying like return or something like that? When we've used the return keyword, and again, remind me, what does the return keyword do? Yeah, makes a function end. Okay, which is probably where the confusion comes from, right? So I've advertised that the return keyword, its most powerful ability is it makes a function end immediately. It also can potentially return a value if it made sense in your program. Okay, so, and this was probably my fault for not showing the additional example. Return is not the only way to get out of a function. Return, the power of it to make a function end immediately is kind of like we would use return to get out of a function early. When we have like a situation higher up in the function, we're like, okay, we're done. I don't need to do anything more in here. I'm going to bail. I got 50 more lines of code beneath me. I don't want to deal with those. You would then put a return there. That gets you out of the function. Otherwise, functions naturally end when they just run out of instructions. Yeah, so when we, this guy right here, when we ran out of things that are indented underneath this, he just ends. We ran out of things to do. He ends. We go back and pick up where we left off inside of main. We print our last thing, and then we run out of things indented under him and there, and he ends. And then since all programs begin and end with main, our whole program is over. All right, that makes some sense? All right, so now, oh, this is going to be a fun one. I'm going to actually stop here for a second. So I'm going to run this again. This is why Python's difficult to teach with. Another example. So same thing we just did, right? I passed in my 5 to some num. I printed it out. It printed out the 5 right there. Then I changed the value to LOL. Not only did I change its value, I changed its type. Okay, you can't do that in strongly typed languages. In a strongly typed language like C, C++, Java, C#, if you've defined a variable as being a number, that is what it holds for the rest of its life, is a number. In this case, not so much. A variable holds stuff. What does it hold? It holds the most recent stuff you put in there. So I started off putting a number in this guy, I printed out a number. Then I passed that number to try to change. That number came in, I printed out that number. Then I changed the value of it to no longer hold a number. Now it holds the string LOL. I printed that out. We see that, yeah, it let me do that. It changed the value of that to LOL. Then this function ended naturally. We got back to main. We printed out the value of X, which was the original value of X, which is 5. So nothing really changed there. We just kind of showed the example that, yes, indeed, Python lets you completely change the type that lives in a variable. Never do that. Just because you can, don't do it. It's a terrible idea. Go ahead.
And variables are global, which is why, like, type print X or like print some num.
Ask that first part. In this case, you said the variables are global. Is that what you said?
No, local. That's why like in that function main, when you say print X, it's always gonna print 5, and then when you say in print or try to change, it's always gonna say print LOL.
I'm gonna say no, that's not entirely true because we're about to break what you just said by passing a different value. You're right, X is a local variable. So start with that. That is true. X lives and dies with main. It is a local variable. It's not accessible outside of the sky unless we hand it to something outside of the sky. That's what we did right here. So it's up here. He's not accessing this X. He's accessing whatever we passed to him, which happened to be the value of X. So we were working with it up here. But really what we're showing here is the difference between pass by value and pass by reference. So what we've seen so far is that numbers are passed by value. Copies get sent in. We don't have to worry about what happens inside of those functions. It's not going to change our original value. Now you might say, well, that's not something I worry about very often, and it probably isn't, especially when you're writing the code, because you have control over what you might do to the variables in your functions. But if you're using somebody else's library that they wrote, because you don't want to have to reinvent the wheel, right? You want to make sure that if I'm going to pass some value that I have to this library, I don't want them breaking my value. I have intentions to use this guy again soon. All right, so we're going to say at this point, primitive types are passed by value. I'm not going to change much here, except I'm going to just work with only strings. So X is LOL. We'll print out X. It'll print out LOL. We'll call try to change. We'll print out some num. It'll print out LOL. We'll change that guy to woot. We'll print out its value now. It'll be woot. Then we come back to main and we print out the value of X. So the question is, will it be woot or will it be the original value LOL? What do you think? You think it'll be woot? Okay. Perfect answer. Strings are object types, right? That's a fact. Strings are object types. In fact, we just looked over in the Java documentation. We saw that strings inherit from object. They are clearly objects. But we use strings a lot. We use strings a lot. So if I go and run this, back to LOL. Okay, so now I'll throw Java under the bus too. If we were back in the 70s and 80s with the C programming language, early strings were abstractions of char arrays. They were called C strings. They weren't our fancy strings we have today. So then we had this thing called the standard template library that had version 2 of strings that also were not like our strings today. Now we have version 3 of strings, which are like our strings today. So the punchline here is that we can start off by saying, yes, all primitive types are passed in by value. Now we ask ourselves, well, how are strings passed around? Well, they're object types. They're not primitive types, so maybe they're passed by address. In fact, I'm going to tell you that most objects are passed by address. So you would be right a majority of the time. In fact, perhaps all the rest of the times. Strings behave differently in most languages. Maybe they shouldn't, because there's actually a mechanism to make it work. I'll go back. I'll swing by and talk about object methods here in a second. But we use strings so often that we effectively are using them as if they're primitive types. Now, why do you think strings are implemented as objects and not primitive types? Why do you think that decision has been made in our modern programming languages? Yeah, it's going to be super common for us to want to do things to strings, right? With primitive types, we're usually only storing a piece of information. But strings were like, okay, I'm going to want to know the length. I want to get stuff at certain buckets in it. I want to convert it to uppercase or to lowercase or to find out if it starts with something or to get a substring. All these different things that strings might be able to do. All those things immediately disqualify it as being a primitive type, right? Primitive types can only hold a value. They don't get all those functions. So since strings are very common and we're going to use them in pretty much every single program, or at least very commonly in programs, and we are very commonly going to be calling functions on them, in a weird roundabout way, I could see a programming language designer saying, well, even though all other objects behave this other way, we'll just make strings behave like primitives. Not the end of the world, but just remember that's the case. All right. So we see that when I passed something in that was a string and I made a change, that change was temporary. Typically, we would call that as having no side effect. So if you're reading that in a textbook or something like that, strings are passed by value as an exception to other objects because they are used so often. What was I just talking about here? Prototypes. Oh, it'll come back to me. All right, so, the side effect thing. So this is often referred to as being passed without the risk of side effect. I mean, it makes sense. Nobody really says that anymore, but I've seen it in a lot of older textbooks where it'll say this either has side effect or doesn't have side effect, which effectively says if you change it, will any other parts of your program notice? Okay, primitive types and strings, other parts of your program will not notice. But we have our class player I wrote up here. Swing back to it. And we have a constructor that sets the name. And we have this do something. I'm actually going to just take that out because it's not related to what I'm doing right now. All right, so I have a really, really simple object here, right? All it does is holds a string. It's actually a good example because it holds a string, which we've seen is passed by value. So I'm going to go ahead and we're going to say X is equal to player Mike. So I'm going to store inside of X, instead of a number, instead of a string, I'm going to put an instance of an object. If I were to print out X right here, what do we expect to be printed? Nope. Why not Mike? What happens when we print out objects? Memory address thingy, right? Okay. We know as humans that this player's name is Mike. That's what we might want it to print. And we'll show you how you can do that, how you can make print behave the way she would want it to behave. Not very often do we actually want to see the memory addresses. Although we did look, I think last class where we wanted to see how they were different addresses when we were returning stuff. So sometimes it's helpful, but not that often. All right, so I'll define X here. I'll go ahead and print out X, which will give me a memory addressy thingy. All right, then I'll call try to change. It'll come in here. I will print out its value. It'll print out a memory addressy thingy. I'll go ahead and change it to woot. Print out something, it'll print out woot. This function will end. We'll bounce back out here. We'll print out whatever it is. So the question is it woot or is it the memory addressy thingy? We see that it's the memory addressy thingy. Well, why? This is an object. Here is that original object. I passed it in. I printed it again. Here is it being printed again. Same object. I'm going to change it to be woot. Print it again. Now it's woot. This function ends. I print out my original. It's back to this. Seemingly, it was passed by value again. Do something here. So now we're going to say, I want to print out x.name. We see that players have a field called name. So now this guy is going to say Mike. Call try to change. We'll print out some num dot name, which will print out Mike again. Then we're going to say some num dot name is equal to Dave. Then we'll print out some num dot name, which should print out Dave. We'll fall out of try to change, and we'll print out x dot name. It was Mike the first time. X dot name was Mike originally. We passed it in. It was still Mike. Mike. We changed that object's field called name. From Mike, we changed it to Dave. Printed it out. Sure enough, it's Dave. But when we came out of this function and we printed it, that change had been permanent. It is now still Dave. Because we were working with a memory address, and what we did is we went to the actual place where the memory address was, and we overwrote the Mike that was stored with that field and put Dave there. So then when we get back here, if I print out X and I print out X there, not X.name, I print out X, we'll see that they're the same memory addresses. So A10, A10. So my memory address didn't change. This is back to the example of you spray painting my house if I tell you where I live, right? We passed the object in, somebody rooted around in an object and started changing names. Later on, when I went back and I looked at that same object, the thing had changed. All right. This would be an example of pass by reference. Why did it not work a few minutes ago when I passed in an object? So when I was passing in, I printed out X, passed in X, printed out X again, printed out that value, changed the, I changed this guy to LOL, printed it out, and then out here I printed it out again. We saw that here it was, we printed it inside the function the first time, then I changed it to LOL, but when I exited back out to main, it was back to the memory address. I'm still passing in an object. Why is it different in this situation? It's explainable. It's not like, oh, this is weird. What am I actually doing right here? If I have a little container here, when I change the name, I picked the thing up out of the container, I manipulated this, I changed the name from Mike to Dave and put it back in there. That was a permanent change. But in this case, what am I doing? I'm saying, okay, I'm going to take this guy, throw an LOL in there. I made it LOL, right? Yeah, so I'm going to take that object out. I'm going to toss it. Now, it still lives in memory though, right? So we have pointers. There's something called a pointer count. So when I create this object, a new memory address is built. And that memory address is stored inside of X. So we're going to say for right now, X points to that place in memory. When I pass X in to try to change, now some num is another variable name that points to the same place in memory. All right. So we have two different variables pointing to the same place in memory. When I picked this thing up and changed the name attribute, the name field from Mike to Dave, I did not change what this variable is pointing to. But when I took this guy out and I threw him away, my pointer count went from a 2 down to a 1. Some num no longer is pointing to this guy. He's now pointing to this other guy over here, which is a string. And in actuality, he is holding the pointer because it is an object. It's just treated with like he is like a bouncer, security guard that follows him around and says, "Hey, you're a string. Just act like a primitive. Trust me, but you're an object." All right. So does that make sense? When we came back to main here and we printed it out, X never lost its pointer. It still always pointed that place in memory. Memory only goes away. We have this thing in most of our modern languages called automatic garbage collection, which effectively is like having a garbage truck driving around in memory, looking for things in memory that have a pointer count of 0. I want to find something that nothing points to, because if nothing points to it, that means there's no way to get to it. And there's no way to get to it, it's just taking up space. So we'll clean it up. In olden days of programming, C++, since you're creating a lot of objects, but it worked for in C as well with arrays. But you would, when you created an object, when you create a mess, it's also your job to clean up the mess. So if you create an instance of something, you then, when you're done using it, it was your job to either deallocate it or delete is in the newest version of C++. It was your job to say, okay, I'm done with that memory. Operating system, you can have it back. Now, lazy programmers don't do that anymore. We just say, look, when I'm done with it, I'm going to leave it out there. It's somebody else's job to clean that up. And sure, the computer accommodates us, makes us lazy. I try that at home. My wife is not a fan. All right. So I know we just covered a lot of stuff, but this is really, really important stuff that connects a lot of the dots together that we've been talking about. Go ahead.
So if you could crack open that last memory address, would it say LOL, like embedded in it, or would it have the previous, like?
No, it would. So if I say print x.name, it would say Mike. Yeah. So the thing that lives at that memory address is not a string. Yeah, we didn't overwrite that memory address to a string. We created this new thing and maybe put it over here at this memory address. So now the what do they call it? Sumnum, this little bucket called sumnum, he now holds a pointer there, no longer up to there. I overwrote where he used to for that one thing. But X still always was holding his pointer up there. So X pointed to that player all day long. You know, we just changed sumnum. Sumnum started off pointing at that guy, and then we change it, and now we make him point to this guy. So for the rest of that function, it still was the LOL thing. But as soon as that function ended and we got back and we're talking about X again, X is pointing to our original player.
Two instances, 3 instances of pointing to the same thing, one to
Two.
LOL, two to original,
Yep.
one to LOL, and then back to it.
Yeah, well, so this is our first pointer pointing to our player. For a moment, sumnum also pointed that same place. So that was 2 pointers there. But then when we overwrote sumnum with a brand new value, we didn't change the value that was there. We said, you no longer hold the pointer there. You now hold a pointer to this other thing in a different place.
And then by the time we drop out, it's just one pointer. The LOL pointer is no longer pointing.
Yeah, because sumnum disappeared. Sumnum was a local variable to this function. So when this function ended, like if I come down here and I try to print out sumnum, it's going to say, I've never heard of that dude. Because sumnum lived and died with that function right there. So LOL's gone too. Automatic garbage collection drove by and said, hey, well, there's nothing pointing to you. You're out of here, bud. Gave the memory back to the operating system. All right. Make some sense? Go ahead.
So, like, is that sort of like the foundation of our method? Like, without
Yeah.
that, we can't really build off.
Okay. Yep. So let's go back to that. So any questions about this pass by value versus pass by reference thing? Just understand that some objects are going to get passed a certain way, some objects are going to get, or some things are going to get passed other ways. You need to be aware of how it might be getting passed in case you make changes to it. Now, the reality is most of the time we're not changing the values of our inputs that are coming in. And if we ever do, it would probably be with objects and we want it to be permanent, you know? So really the default behavior is likely the behavior that you want it to be anyways. So really this isn't one of those things that was going to bite you very often. Probably falls into that similar category to how often you run into time complexity problems. But it's one of those things where like, well, why the heck is it doing this? And if any of you have ever taken a C or C++ class using old school arrays, you've definitely run into this with arrays. Anybody in here have either a C or a C++ class where you worked with arrays? I remember when I was first introducing lists, somebody said, is that like an array? Let me write something out here.
Well, here, arrays are also.
All right. So I'm here. I'm going to throw some random C++ code out in the middle here. And we're going to say int pointer AR2 is equal to all right. Does that look like anything anybody in here has seen? What I have highlighted there?
Just the first one.
Okay. But so let me just abstractly talk about it because it does tell a story here. So this is C++ code. These little star things here, that's the special syntax we have for pointers. In older languages, we got to choose whether we wanted something to be passed by value or passed by address. In older language, we could have said, hey, hold the house. We get to choose to do that. We can choose whether to pass the pointer or not. Modern languages just make the decision for us and say, look, you're never passing a house. Deal. All right. All three, well, the first two lines do literally the identical thing. The new keyword is like our real estate agent. We can say that that's kind of implied right here. Python doesn't use the new keyword, but we've seen that it goes and gets us memory addressy things. So we are clearly getting a memory address from this line right here. So that whenever you see the new keyword in other languages, which is super common in other languages, the result will be a memory address. So this guy right here is creating enough memory to hold 20 of those guys in contiguous memory, which we talked about, memory right next to each other. Okay, the second guy here is just the more intimidating version of the same thing because we are allocating our own memory rather than using the new keyword. We're saying, look, I want to create an integer pointer and I want to put in that integer pointer. Go ahead and allocate me some memory big enough to hold 20 of these guys. Now he'll come out of there as something called a void pointer, but I'll just go ahead and say, just treat him as an integer pointer. That's what he is. That just tells you as you're walking through contiguous memory, how big of the steps you take when you go from bucket 0 to bucket 1. If it's chars, you take a 1 byte step. If it's an int, you take 4 byte steps as you walk through it. If it's a void pointer, you're just taking steps. So it'll give you some weird errors. It'll only work if it's chars. But now this last line here, this is where the kicker comes in. So I'm going to tell you anyways, in case you run into this as you're typing in code or whatever. A common understanding for C programmers is that this third line is like a shortcut for the first two lines. I sometimes will call that syntactic sugar. It kind of makes it easier for you to write it just a little bit shorter, like, oh, I'm going to write collections. But this guy creates a local memory address. So when he's passed around, it's passed by value. These guys have a global memory address. When they're passed around, they're passed by address. So very common mistake for beginning programmers who use a language like C or C++, because that third one is not a shortcut for the other two. 98% of the time, it probably will behave the same for the way you're actually going to use it. But that one time that you pass it around and you're just, why isn't things changing? That's the reason why. Tuck that in the back of your head somewhere. All right. Questions, comments, concerns, bribes? Say this again.
So it's the basic like, the method.
Yeah. So init is what we call our constructors, and we're going to start by going back down into init next time. But init, this guy right here, is how Python handles constructors. Other languages often make you name the constructor the same name as the class.
Yeah, because I do Java and that's what I recognize.
It's the same identical thing. They're accomplishing the same job, just Python says you got to call it underscore init. Java says you have to call it the same thing as your name as your class. Yep.
Where's the practice exam? Where does that live?